Hello, my name is Christiane Gillner and today I would like to introduce aerogels to you. Aerogels are highly porous materials and therefore they create a good basis for insulation materials. There exists a lot of different types of aerogels depending on the material they are based on. I will present you two aerogels that are quite similar but have different acoustic properties. First, I would like to give an overview about the main properties of aerogels. As already mentioned, they are highly porous materials and can reach porosities up to 99.9%. This results in low densities in a range from 5 to 200 kilograms per cubic meter. The pore sizes of aerogels vary in a range from nanometers to micrometers. Therefore, aerogels have large internal surfaces compared to their volume, which makes them good thermal insulation materials. From a mechanical point of view, they can vary from fragile up to extremely flexible. Their surface can be hydrophobic or hydrophilic. And of course, they also have good acoustic properties. Aerogels are manufactured in a so-called sol-gel process. The main ingredients of this process are alkoxides, which will form the structure of the porous material, alcohol, water, and catalysts. In the first step, all liquid compounds are mixed. This leads to the second step, a formation of a network, which is called the gel. And in the last step, the solvent needs to be removed from the pores. This is also named the drying. For the aerogels discussed in this presentation, the drying can be done at room temperature. Small changes in this routine of the synthesis can result in another material. For example, you can change the temperature or pH value of the ingredients. Another possibility is to change the amount of the ingredients. In the following, we will discuss two materials with different amount of alkoxide but the same amount of the other compounds. Reducing the percentage of the alkoxide with the same volume of the other ingredients, the resulting material has definitely a lower density, and we will see that also other parameters are influenced by this change. Here you see the two flexible aerogels we will talk about. Starting with one recipe for the preparation of an aerogel, we got the sample on the left side, which is called basic in the following. It has a density of 110 kilograms per cubic meter. A reduction of the amount of alkoxides leads to the second sample on the right side, in the following called diluted. It has a density of only 70 grams per cubic meter. Just by eye, they look the same. But if you touch it, you will realize that the diluted one is a little more fragile than basic. For the characterization of the acoustic properties, I chose the absorption coefficient. To define the absorption coefficient, I made impedance tube measurements up to 1600 Hz. Both samples have a thickness of 9 mm. I made measurements with one layer and two layers of each sample. In blue, you can see the absorption coefficient of one layer, and in red for two layers. As one would expect, the absorption coefficient of two layers is higher than for one layer due to the higher mass. But for the basic sample, the difference between one and two layers at higher frequencies is quite low. Comparing diluted with basic, the absorption for one layer is lower at all frequencies. But two layers of diluted show a different behavior in the higher frequency range than the basic material. This leads to the assumption that the acoustic properties of these materials are not the same. To get an idea what might be the differences of these materials, I set up a numerical simulation. In the simulation, I represented the impedance tube measurements with both 1 and 2 layers of each sample. Here, the dashed lines show the results of the simulation. They match quite well with the measurements. Therefore, I can use the simulation to identify some of the acoustic parameters of these samples. For the simulation, I used the material model from Bio, which is a quite common model for the description of porous materials. The included parameters are the density, the flow resistivity, the viscous and thermal lengths, which describe the size of the connection of two pores and the diameter of the pores, the porosity and tortuosity. I measured the density of the samples and determined the other parameters by inverse characterization, which means I compared the simulation results to the measurements. The main difference between basic and diluted is the flow resistivity. With the lower density, diluted has a flow resistivity only half the size as basic. This is the parameter with the largest influence on the measured absorption coefficient. Another important parameter is the viscous length. The viscous length of the diluted sample is a little bit larger than for the basic sample. This makes sense as for the same volume of liquids, less structure was available to form the network, and the resulting pores therefore need to be larger. Only small influence on the absorption coefficient have thermal length, porosity, and tortuosity. The thermal length is larger for diluted because of the same reason as for the viscous length. The porosity of diluted is a little bit higher due to the lower density. The tortuosity might be similar for both samples. In the next step, we combined both materials. So far, we knew that the density is not the main parameter for the absorption coefficient. Therefore, we wanted to know if you can reduce the mass of an isolation material by a combination of two materials and still get a good absorption. For the combination of both materials, I used again the setup with the impedance tube. I used one layer of each material and changed the layout so that both samples are once placed in front. Here you can see the results of the simulation. I also did the measurements, which show the same behavior. The results are compared with two layers of each sample. In blue, you can see the absorption coefficient for two layers of basic. In light blue, you see one layer of basic with one layer of diluted. The resulting absorption coefficients are nearly the same, although the mass of the combined layout is lower. The same behavior is visible if you switch the samples and place one layer of diluted before one layer of basic. This you can see in the yellow curve and compared to the red curve, which is for two layers of diluted. It appears that the front sample is the main reason for the resulting absorption, and it might be possible to reduce the mass by using a combination of both materials. Or If you focus on high frequency range but try to reduce space, it might be interesting to use diluted in front of basic. But we need to keep in mind that for this setup we have straight sound incidence, and the effect might be smaller in more complex applications. Therefore, I set up a simulation with a diffuse field excitation. The application we chose for this is the sound transmission through an airplane fuselage. It is a part of an A340 with a dimension of around 1 meter times 1.2 meter. As already mentioned, the excitation is a diffuse field. The model includes an isolation material of 100 mm thickness, which you can see here in blue and red with each 15 mm thickness. The same material combinations as before were investigated, which means 2 times basic, 2 times diluted, and the combination of both with once basic in front and once diluted as front sample. For all material combinations, the transmission loss is calculated. First, I want to compare the transmission loss of only the structure with the diluted aerogel. The transmission loss without any isolation you can see in the dashed black curve. By adding isolation material with 100 mm thickness of diluted, you get the red curve. The transmission loss is of course higher due to the higher mass. To analyze the effect of the mass, I added the mass of the isolation to the structure by changing the density of the structure. The resulting transmission loss in the black curve only shows a constant offset through the whole frequency range, whereas the aerogel yields a higher transmission loss, especially at higher frequencies. The results show that the aerogels not only have good acoustic properties due to their mass, but due to their porous properties. Now, let's have a look at the results of the other material combinations. In blue, you see 2 times basic, in light blue basic and diluted, and in yellow diluted and basic. In the lower frequency range, up to 350 Hz, we see the same behavior as for the straight sound incidence. The combination of basic and diluted yields the same transmission loss as 2 times basic, and also diluted and basic yields the same transmission loss as 2 times diluted. We also see that in the higher frequencies, the mass of the material has the largest influence on the transmission loss. At 1000 Hz, the transmission loss of both combined materials is the same, and it's between the pure basic and pure diluted material. So we can see that the layout of aerogels can influence the acoustic behavior also with diffuse field excitation. In summary, I introduced you into a small part of the possibilities of flexible aerogels. They can be good acoustic absorbers, and only small changes in the synthesis can strongly influence their acoustic properties. We also saw that combinations of different materials might be a possibility to reduce mass or space in some applications without reducing the absorption properties. For the next steps, we would like to reproduce the results of the diffuse field simulation, and we would like to examine inhomogeneous aerogels. For example, add holes of air inside the material directly during the synthesis and see how this can influence the acoustic properties of aerogels. And with this, I would like to thank you for your attention, and I'm happy to answer your questions.